welcome back. Today's lesson is going to be for Thursday, the 26th, and we're going to finish up some notes today. Get through a lot of the information, and then we're going to need to do some massive amounts of practicing. So I've thrown a lot of information at you, and I understand that, but sometimes all this stuff is so connected that it's hard to practice in isolation. So it's better to get all the information and then kind of move forward and do our practice from that. So again, this is going to be for Thursday, the 26th, okay? All right, so we left off with our last session looking at groups and periods. So I want to give you some visuals and help you kind of put this hopefully into a little bit better understanding for you. So our periods, we said you read just like you're reading a page. So those are going to be the horizontal rows. And I like this color, that really helps me. I know I'm pretty visual with things. So the periods are going to be those horizontal rows. On your periodic table, you will see that I had in red, it says periods, and then 1, 2, 3, 4, 5, 6, 7. Those are going to be important. We don't really include these bottom rows, and we'll talk about why that is later. But 1, 2, 3, 4, 5, 6, 7. That is important. You'll also see it on this side as well, because sometimes people forget hydrogen and helium way up here in red, and you'll start the period down here, 1, 2, 3, 4, 5, 6, and that gets you off of a period or a row, and that is can cause some big mistakes. All right, so just be careful to not forget poor hydrogen and helium that are left up there. And we'll talk about why they are here in a minute too. Okay, so then obviously our groups are going to be our vertical. Okay, and again, color coded. Now notice, you skip all this stuff in white. The reason you're skipping these are actually called transition metals. They are not predictable in the number of electrons that they will give away. All right, so because they're not predictable, we have to leave them in their own kind of category, but all of these tall columns that I'll say, so these are the short ones, they're not predictable. These 8 are. They're extremely predictable except for group 4, and we'll talk about that, why that is here in a minute, okay? But you'll notice, these ones are not colored in. They are not considered part of our valence electrons because they don't behave predictably. And again, as we get all the information, all of this starts making sense. I know that there's a lot that's involved with this. And again, if you need to replay this lesson, that's the beauty of having it on video. You can watch it as many times as you need, and then maybe form good questions, and you can email me and I can clear up anything if you can't figure it out at that point. All right, so here it says groups, and now I just kind of contradicted myself because here it's counting all of them, right? All the short ones. So there's actually 2 sets of groups. There's going to be one that includes all 18 columns, okay? Those are our total number of electrons. If it's just counting valence electrons, we do not include, mark these out, we do not include the transition metals, all right? And so we still would have we would still have 1, 2, and then here we would have 3, 4, 5, 6, 7, and 8. Notice how once you cross the transition metals, there's actually 10 columns. And so it's like we're subtracting by 10. So if we're talking valence electrons only, and if you look at your periodic table, in valence I have that for green, and it has my handwriting, and they're circled and they're highlighted green. So 1, 2, you skip the transition, and then 3, 4, 5, 6, 7, 8. Then if you look at the yellow, which is groups 1 through 18, just like up here, you see 1 all the way to 18, and it's because you're including all of these 10 transition metals as well. So it's not like we want to just totally ignore permanently these transition metals. Depending on the situation and depending on the wording and depending on the problem, sometimes you just care about the valence and you'll say groups 1 through 8 or valence. If you are talking about all of the groups, then you'll just say total electrons. So total electrons means all columns 1 through 18. If it's just valence electrons, you'll be dealing with just the tall columns 1 through 8. And that's when we kind of ignore temporarily those transition metals. Down here, you'll see that the lanthanides and the actinides, they actually fit in right here. These were discovered after the periodic table was more arranged. And so they actually fit in here. And so they kind of have them just drop down. And so that's why you'll see them separate from them fitting in. And you'll see the gap. You'll see 57, and then it goes 58, 59, and then it goes 71, and then picks right back up with 72. So it's kind of like these need to fit right in here. And then the same thing down here with the actinides, 89 to 90, and then 103, and then you pick up again with 104. We're not going to deal with those. As you get into higher level chemistries and stuff, obviously you will, but this is an introduction. So all of this we're trying to keep very simple and very straightforward, and it's still a lot of information, okay? So again, your periodic table, I think sometimes that actually helps make these group 1 through 18 for total electrons, and you'll see that, so just your normal groups in yellow, 1 through 18, and then your valence groups in green that are circled at the top, and you can see that key. And I have 1 through 8 listed to show you that difference, okay? Most of the time, we're going to be dealing with valence electrons, and certainly next unit when we get into bonding, that's really all we're concerned about. But you still need to realize that there are a total of 18 columns or 18 groups because, you know, these metals are important. It's just they're not very as predictable, and so for us, we're trying to deal with the easy things, things that are predictable, and so it's easier for us to kind of assume that we can ignore these for the moment. Okay, so valence electrons. These are the electrons that are in the outermost energy level. So again, if we're talking about Niels Bohr's model, you know, he shows them in these nice even levels, shells, layers, you'll hear them called. And so the valence are going to be the ones that are on the outermost area. And think about it. If the electrons that are in the outermost area, they're the ones that are most likely to get taken, or that's the area that are most likely to gain electrons. You're not going to fight through all those layers and steal electrons from the inside. They're going to take electrons from the outside. Excuse me. Okay, and so because the valence electrons are in the outermost area, it makes sense that they would be the ones that are going to react with other elements. Because this is, remember last unit when we said kind of generically like the attractive forces between molecules? Well, it has to do with the electrons that are getting passed back and forth, or maybe even shared. So here, carbon has the electron shown in blue. So carbon has 4 electrons, but to be balanced and satisfied, they need 6 because carbon has 6 protons. So it's really trying to gain some more hydrogens, and so, or gain some more electrons. So hydrogen is also wanting to get balanced and satisfied. And we'll talk more about that here in the future, so don't get too overwhelmed. But it's showing that the electrons in the outermost part of the hydrogen are going to come and buddy up with the electrons in the outermost area of the carbon, and then it makes the carbon happy and it makes the hydrogen happy, and then everybody's happy and satisfied, and that's the way elements want to be. Okay, and so again, thinking of the valence, they're the ones in the outermost energy level, so it makes sense that they would be the ones that get to interact first. Okay. So remember that the elements in the same group or vertical column have the same similar properties, and that they're arranged by the number of electrons that they have. So here's the arrangement. All of these are going to have 1 electron in the outer area. All of these will have 2 in the outer area. 3, 4, 5, 6, 7. Notice helium. It is a 2, which you would expect would be over here. But because hydrogen and helium are so small, and that's why they're kind of up here on their islands by themselves, they're so small because hydrogen has 1 proton, helium has 2, and so it can't hold any more than 2. So all of these are called noble gases over here. And if you're considered a noble gas, it's because you have a full outer valence. Well, helium's so small that 2 is as full as it gets. It's unique, it's the only one like that. All the others are big enough that they have 8 in their outer shell. So having just 2 here fills it, even though over here 2 isn't full, because these elements are big enough that they can actually be full at 8. All right, so helium is special, and as we get into this, this will make a little bit more sense. Okay. So valence electrons can also be thought of as the number of electrons that the atom needs to gain or to lose to be stable and satisfied. So there's something called the octet rule. And in the song you heard a stable octet. Stable means satisfied, everybody's happy and good. So the goal is to always have a full octet, meaning you're trying to either get 2 if you're helium or 8 if you're any other type of element on the table. All right, and so here you are 7 away from being at your 8. So is it easier, do you think, to get rid of 1 electron or to try to gain 7 to reach your 8? Because if you get rid of 1, then you back down to the next energy level. Okay, because these are all kind of like levels and rows. So as you go across, you drop down and come back. You go across, you drop down and then come back. Go across, drop down and come back. So if you're here and you only have 1 extra electron, if you could get rid of that extra electron, you would drop down and go back, and now you're full. All right, so we'll get into that quite a bit. So it's those valence electrons that tell us how many electrons they need to get rid of or how many they need to gain to get to their full energy level. Okay. So besides looking at the number of electrons, the vertical columns, right, and the number of protons that are the horizontal columns, there's other information that the periodic table shows us, because certain elements are going to share properties that allow us to classify them even further. So group 1, or the alkali metals and the alkaline, they have certain properties. The non-metals that are on the right-hand side of the table, they have similar properties, and then the metalloids are kind of that transition between the metal and the metalloid, or the metal and the non-metals, excuse me. Then we have a group called the halogens, and then I have already mentioned the noble gases. You're going to need to know these areas and where they would be found on the periodic table. All right, so first some characteristics of metals. Obviously they're shiny, they're malleable, meaning you can bend them. They conduct heat and electricity well. They have a high melting point, high density. And here are our metals in those bluish gray color. All right, so a lot of metals. Again, it's showing groups 1 through 18, and it's showing periods 1 through 7. Alkali are group 1. They are very reactive. They do not occur freely in nature because they are very unsatisfied. Like, all they have to do is get rid of that 1 electron and they would be back to being a noble gas, and they'd be nice and stable and solid. Not like states of matter solid, but stable, I guess. And so they're going to react very rapidly, so we don't even find them naturally occurring in nature because they react so quickly. They are going to give up 1 electron. And if they give that 1 electron through bonding, then they are now satisfied in their outer valence because you drop down a level and that level was full. Because each level keeps filling up with electrons until it's full, and then you start a new energy level. And then when that level's full, you form the next energy level. And when that energy level's full, you form another one. So if you drop down, that one was already full, or you wouldn't have stepped up to the next energy level. Okay. So lithium, sodium, potassium, rubidium, cesium, and francium. Right here. Hydrogen remember, hydrogen and helium are up there and they're islands kind of by themselves. They're where they are because of their number of protons, because their number of valence electrons, but they don't actually fit all the descriptions. So like the hydrogen is not considered an alkali metal just because it is so small, but it fits here because it has one valence electron. So hydrogen and helium are kind of those oddballs that don't totally fit the pattern, but the rest of them all fit perfectly. So all of these I could predict are going to give away one valence electron, and then they would drop down to the next energy level, which was already full. That takes us to alkaline. They are found in group 1 of the periodic table. They are extremely reactive as well. Just a little less reactive than the alkali though. They do not occur freely in nature. Again, they react too quickly for that to happen. And they're going to give 2 electrons. They give up 2, then they drop down to their inner energy level, and that was already full and stable. And so they readily will lose those 2. And here we have beryllium, magnesium, calcium, strontium, barium, and radium. These are our alkaline. Now, one way to remember the difference between alkali and alkaline, let's see, it kind of, the I at the end kind of looks like the 1 for group 1, okay? That's one way. And then the alkali, the I comes before the letter N, and the group 1 comes before a group 2. So alkali has an I, looks like group 1. The letter I comes before the N, like if you had finished that word of alkaline, right? The N comes after the I, just like the 2 comes after the 1. So the alkali, then the alkaline. Nonmetals. This is where you have solids, usually that are dull, brittle, they don't conduct heat or electricity well, they will gain electrons, that means they're going to take them, and they have low density and a low melting point. But the key here is they gain electrons, they're the takers. Metals are the givers. So here's my metals, and again, we're showing groups 1 through 18 here. Our nonmetals are usually right here. And you can see it kind of staggers. You're finishing out your metals. These are kind of your metalloid area. We'll talk about those in just a second. But the majority are going to be metals. And then you have metalloids, which kind of have properties of both. Okay, metalloids are semiconductors. They have both properties, and so like silicon, it's super important, like in the computer chip industry, because sometimes they can conduct heat. Sometimes they don't, and so like they can use those properties to help make things pretty convenient, where you don't want just a metal and you don't want just a non-metal. Okay. And here are the metalloids, and it makes sense that they are the border between the metals and the non-metals.
Mrs. Tobin, if you're in the building, would you please come to the counselor's office? Mrs. Tobin, if you're in the building, would you please come to the counselor's office?